Debabrata Panda.
Good afternoon, everyone. Glad to see you all of you here. And thanks for waiting quite long until the end to hear at least some people who are presenting the end. Myself, Debabrata Panda, and representing IPGP and PFAS. And of course, you can see the heading is like ultrasonic cavitation technology for on-site treatment of PFAS contaminated groundwater. So this is an interesting work, but we started with lab scale investigation first. So I will go slow, and I'm not going to complicate the things, so you can understand it more interesting. So we started with only PFAS. So I don't have to introduce this. Of course, everyone knows about PFAS here and how the European regions are getting more contaminated and what are the sources, and just for some fun, like you can have some the news, what is coming up, and probably you see some of the European officials also test positive for forever chemicals. Probably have to do the best here to prevent the contamination and put more stringent laws to prevent its spreading. Going further, I will just describe what we are doing now and what is the future of the work. So we started with large-scale feasibility experiment, starting with PFAS, and that under optimum sonochemical conditions. So what is sonochemical conditions? What is sonochemical experiment? You will see in the next slides. So also it is very vital to determine the electrical energy order to understand its feasibility for upscaling and also the calorimetric yield calculations. So we can compare the work in a right way, wherever previously did the work, or to compare the work with other advanced oxidation methods to understand whether this technology could be eligible for upscaling, what are the energy efficiencies, and whether how it will cost in industrial scale applications or real life environments. So our work is now to, of course, show you what we did with PFAS. After that, the challenges still remain for the upscaling design and the effectiveness study, and to understand how the sonochemical method could work on complicated contaminated groundwater across Europe. So starting with this is I have given some details about the large-scale feasibility study we did with the PFAS. So here is you can see the large-scale instruments that has been provided by Synaptech, is our industrial partner who has been giving us the sonochemical experimental requirement in terms of all these reactors, generators. So we started with PFAS and we did the analysis for LCMS to understand the compounds removal, and also we did IC analysis to understand the fluoride evolution or defluorination. It is very important to understand not only the degradation, also the mineralization. So to compare both the outcome, we did LCMS as well as IC analysis. So we did also the two frequencies. What is sonochemical experiment? There is different frequencies available for the treatment. So we did low frequency and high frequency. So depending on the frequency, the effectiveness of the treatment might alter, might change. So to understand the difference between the frequencies, we considered a low and a high frequency. High frequency is 500 kilowatts, the low frequency is 20 kilowatts. The power density is quite important to understand the effectiveness of sonochemical method. So we varied the parameters. We consider different concentrations starting from 2 microgram per liter to 5 milligram per liter. We did different temperatures. We maintained the reaction solution temperature in a different, like 20 to 40 degree. Solution volume 100 to 500 ml and treatment durations. So that is also a vital factor. 3 hours has been ideally considered for the study now. Also, we did for 240 minutes, 4 hours for some groundwater samples that we are still working on. Moving further, this is a generalized setup overview. But you can see here, there is a reactor and that it has been connected to a thermostat that maintains the reaction solution temperature. It has been connected to a PC, and there is a software that will monitor the overall frequency, what has been working on the reactor. We maintain the solution temperature, through the software. So this is the integrated system. Through the software, it is very easy to monitor the reaction because we can change the power level, we can change the solution temperature if we see if it's changing, we can monitor it. So this way, it becomes much more efficient, much more accurate. So this is one of the first sonochemical experiment that has the next gen software, and we do that in an integrated way. So moving further, it's not much here to show, but it's very precise so that you can understand very easily. So the outcome after the PFAS experiment with all different parameters, everything, 100% could be removed within 3 hours with the optimum conditions like power density and the solution temperature that I already have mentioned. And also the dechlorination ratio could reach until 99%. And also we did some calorimetric study to understand the yield that has been how much we are drawing the power and how much we are actually delivering to the reaction. That is very important. You might have drawing like you might have 100 watt, but you are not drawing it to 100 watt, probably because it's lost in there. So it's a calorimetric experiment is very important to understand the yield. So we have a 30% yield. That means if you are drawing 100 watts, we are using 30 watts. In this way, we compare our outcome to previous studies also. So that is in the next, I will show you also. Here is a very precise outcome. What I can show you, the side A is has been taken for the mass spec analysis, how the concentration has been declining over the time from A to E or H. You can see that the initial concentration has declined over the time, and the side B, you can see the fluoride evolution that has increased over time. So that means exactly what should happen. So the concentration should decline and the fluoride evolution should increase. That tells the compound is getting mineralized, not only degraded. That means any byproducts remaining also that is getting mineralized. So this gives a very definitive outcome that you see within just 180 minutes, like 3 hour treatment, you can be able to reduce the concentration to until like 100%, and it's also you can get mineralization like 99% under optimum conditions. So I just want to emphasize like how ultrasound work. It works like it creates bubbles. It creates bubbles based on the frequencies. Based on the frequency, the bubble size could vary, and it explodes. It like implodes over the time. This very frequently. So whenever the pollutants, any kind of pollutants, like example here is PFAS. So enter into the liquid phase or the gas phase or the interfacial phase, depending on the pollutant, depending on its nature, it could enter the different phases of the bubble. So bubble mechanics, bubble things, if you read more about sonochemical methods, you will understand how the bubble work and how the different pollutants get degraded. So in this case, we get within 3 hours, we can see like 5 milligram per liter, 10 milligram that kind of could degrade, could mineralize. That means it's not just working on advanced oxidation like reactive stress is best. Also, there should be some thermal degradation that works in the interfacial region and could also enter into the gaseous phase that could mineralize the pollutant without leaving behind any byproducts. So this outcome that we got is really excellent. That we compared also, we got like PEO, we determined it like 700 kilowatt hour per meter cube. That is compared to one work that is cited here, the down 2023 has been published, and we compared them, and we see that our outcome and our electrical energy order is quite low, but we get much more efficient. So it says like our reaction that is higher is because of probably we are monitoring it quite well. Probably also how the reactor has been designed, like based on the company, how the reactor designed, how the material is there. So that also depends, like how intense the cavitation should be generated. So overall things we can say it's quite impressive what we get. So for the upcoming work that we are working on now, we are with some Spanish groundwater samples and others we are working on now. And we got some good outcome, but we haven't presented here because we're still working on that. So it is also quite working well in different groundwater samples that we are evaluating. So now we are working on the synaptoid to upscale the technology for the real world applications and also performing different sites and different groundwater samples that we are receiving. So we'll finalize the prototype within the next year of time. So yeah, this much for now, and thank you so much for your time.